Hi everyone, my name is Julien. I'll spare you my last name.
Oh, come on, I'm trying to pronounce it.
So as some of you may know, there was a pandemic in the rest of the world, not in this state, I heard. And it really changed a lot of things in the industry. And so today I'm going to talk about indoor air quality and the recent changes that happened in there and how it relates to HVAC infrastructure and how the two interact together. Feel free to interrupt me if you have any questions during the presentation. Otherwise, we can just go ahead. Okay, I guess I can skip all these things. Okay, so I'm going to spend a lot of time talking about indoor air quality and the different metrics and what they mean and why they're important and how they tie to HVAC systems through different case studies. Okay, so before we actually go in there, I want to talk a little bit about my background because it kind of relates to what's going on now. So I did my PhD in biomedical engineering. So when I finished my master, a medical doctor works on Parkinson's disease, came to my presentation, and I was working on networks of sensors. And he said, would it be possible to use accelerometers to help better understand Parkinson's disease and better assess the severity of the disease? Because the problem now is that we make the patient do a certain list of tasks, and we look at it, and then we score it, and that's it. And then if you ask different doctors to score a patient, they will give a different score, and even the same doctor doing the same patient might give you different scores as well. And so he was looking for a way to have better quantification of what was going on. And so what we did is that we placed accelerometers on the body of patients, made them do the same exact test, collected data, extracted patterns, created models to better detect things that they wouldn't be able to detect with the naked eye, and actually try to predict those scores more accurately. And why it matters, because it's the same thing that happens in our industry where it's a status quo. People walk around in buildings and do spot checks. Once a year they will get the bills for the year or do a indoor air quality inspection. And we could use technology to do things better. I'll go in more details later. And then the second thing we did after that was, okay, now we have real-time data, we have real-time patterns. What do you do to treat the patients? So to treat the patient, there's different techniques, but one of them is called TMS, transcranial magnetic stimulation. And so basically you place a magnet on the brain of the patient, and then you do stimulation, and the patient will start doing weird movements, which I tried myself and it was weird. And basically that stimulates the brain and that reduces their symptoms for a little bit. And the problem is that now it's kind of applied blindly. You don't really know what's the effect, and it's hard to quantify. So same thing, we use the sensor to detect when it should be applied because the symptoms are getting worse, and then you apply it and you see the effect. So same thing in buildings now. We run our HVAC because it's too hot or too cold, but we don't know what's the impact on things other than temperature, right? We don't know what's the impact on CO2, on particulate matter, and so on. And so the same exact principles that I used in my PhD, now I'm using in our space in buildings, just with a different data set. And that's really what my company and one of the co-founders were doing, is that we're bringing data from the physical world to the cloud so people can do this type of analysis. And so the way we're doing that, and I want to talk about it because it will shed some light as I explain things. So we created a system where we sensor agnostic. So we don't really care what sensor we collect data from. We create the whole pipeline to bring the data to the cloud. And why it matters? Because technology these days changes very rapidly, right? And you've seen probably it with COVID, there was no real sensor to detect pathogens in the air before. It was super expensive. It was stuff that the army uses. Now there's a lot of companies who are doing R&D and trying to bring those types of sensor in buildings. And it's really hard for the industry to adapt to that. So we're trying to develop technology to do that. And the quality of the data that you get to do your analysis really matters, as you know, right? You're always trying to look for instruments that are very accurate. Otherwise, any analysis you do is garbage. And so that's what we do. And then with that data, you can, most of the time you will do a report because that's, what the end customer pays you for. But more and more, there's public awareness and people want to know what's going on around them. They go in a building, they want to know lead, what's the lead rating? They want to know what's the air they're breathing. They want to know, did they upgrade their filters? They want to know all those things in real time. And so that's a trend that we really see from our customers where they not only need the data for the building engineer so they cannot manage the building, they need the data for the tenants, for the public and whatnot. And so that has a direct impact in the technology that people use because it's not just about, have a backnet indoor air quality device connecting to the BMS and nobody can see the data. It's much more than that. So a little bit about history of indoor air quality first. So when we started our company in 2014, really everything people cared about was temperature and humidity, right? It was really the state of that industry at that time. Then people started realizing that CO2 matters, right? And then you had a lot of demand ventilation control and stuff like that. So we started developing modules with CO2 sensors. I'll talk about that more in a minute. Then climate change, a lot of wildfires, started getting a lot of requests for, okay, it smells smoky in the building, why? Well, all those wildfires generate a lot of smoke, goes inside the HVAC system, inside the building, and it has an impact. What impact? We'll talk about that. And then from there, it just, grew very rapidly, even faster with COVID, where people really care about, what's going on with the air they breathe, what's coming inside the building. We try to lower energy, so run HVAC system less. What's the impact? We try to seal buildings to save energy. What's the impact? All that we're seeing now, some changes and some things that were not really always intended. So, as I mentioned, air quality has always been of interest, mainly because it has an impact on our health. That's really what's driving it. And it's been accelerated lately with newer technologies like IoT and then COVID over the last couple of years. And so the people need to feel safe, right? The only reason they would come back to spaces is because they feel safe that building operators took measures to make the space safer, right? So, change filtration, increase ventilation, and whatnot. And so to do that, they need to have data. And so that's some of the data that I took to present today. So I'm going to talk about 4 things. Air filtration, and what it means and what's the impact on HVAC equipment. NeedlePoint Bipolar Ionization, which is a technique, I don't know if you guys are familiar with this, but that you release ion in the air and it's supposed to attach to VOCs and particulate matter, make them heavier and easier to filter. And also the impact on HVAC. And then ventilation and CO2 in schools. Same thing, what's the impact, and then some notes on IAQ scores. And I don't know how familiar you guys are with indoor air quality, so hopefully I'm not saying too many things you know or you have no idea what I'm talking about. So feel free to ask questions. So you guys know in buildings we put filters, and the main reason we put filters is just to clean whatever is in the air, right? There's pollution outside, whatnot, so we put filters. What do the filters do? They basically are a mesh of some sort. They block the particles. There's a little bit of a drop in pressure because of that, so that's why you need fans also to push the air through those fans into the building. So that's fine. The problem with COVID is that people realize that the size of the particles that carry the virus are actually much smaller than what we're used to. Right, so when you look at typical pollution particles, is 2.5 micron to 10 micron. That's why people always talk about PM 2.5 and PM 10. That's the size of the particles, 2.5 micron to 10 microns. But with the virus, now we're looking at particle size 0.3, 0.5, 1 micron. And ASHRAE came out and said, okay, we need to upgrade the filters to MERV 13 and higher to filter those particles. So ASHRAE says it, everybody does it. The problem is that those filters have a much tighter mesh, and so they block the air a lot more. And so you can't just go and change your filter. You actually have to make sure that your fans can actually push the air and not burn out because they just can't handle this type of consumption. So some building couldn't do it, some building just did it and then had a lot of issues. And the way we tell our customers to do it is just put sensors, right? So look at the differential pressure on your regular filter and the power consumption of your HVAC equipment, and then change your filter and see what's the impact. Right? So you make sure that you're not going to destroy your equipment, because not all buildings and not all HVAC equipment can handle having a MERV 13 on them. The next thing you need to do is actually see what's in your air, right? Because it's not about, oh, I'm putting a MERV 13, I'm good. I don't have to do anything else. No. And so I'm going to talk about that. So here is a map of the US. I think it's from last summer. And we are based close to Washington, DC. Can you see the mouse on this thing or not? Nope. Well, so, yeah. So we're based here. And there was a lot of wildfires on the West Coast and up here. And this is a map of the EPA. And you can see the gray stuff is the propagation of the smoke through the atmosphere, right? So although we don't have wildfire here, all that smoke is going there. And I don't look at EPA maps all day long, so I actually went back and saw that after the fact. But what I saw is this. So the top chart is a school in Washington, D.C., and the bottom graph is a Class A building 2 blocks away. The blue line is the outside air, particulate matter, and the black line is the supply air, particulate matter. So you see our schools are great. They follow very well the pollution from outside to the inside. That's what our kids are breathing. And then on the other side, on the Class A building, you see nothing. The air is super well filtered. So it was last summer, right? So it was through the pandemic after, we took measures to make our building safer. So this customer was really good at it. I think they put a MERV 15 on their outside air and then MERV 13 throughout on HVAC system. So they do a good job, and so all that pollution from the outside is getting removed from the building. So same thing with all the indoor pollution. But on the schools, where they didn't really take measure. I think they did just some HEPA filters in the rooms, like portable units. So that doesn't have an impact too much on the outside air, but you can see how terrible it is, and that correlation between the two curves. And by the way, just to give you a scale, this is 10, 20, 30, 40 micrograms per cubic meter. The EPA recommends to be lower than 12 on an 8-hour average, right? Which is like here. So you see that a lot of days inside the building, we're breathing more than what the EPA recommends for outdoor exposure.
Can you use your pointer over here too?
Yes. I don't know, it's a weird setup.
Can you use a cursor on the laptop?
I tried, but it didn't.
It doesn't
Not work. So yeah, I was saying, so this is 10, 20, 30, 40, so 12 is here. And so the blue lines are the outside air, the black line, the supply air inside the building. And so you can see how here it's pretty bad, versus here in the Class A building, you can barely see the black lines. It's good, you're gonna make me walk. No, it's good. Yeah, exactly. So, so particulate matter is not easy to understand. So imagine you have particles of different size, like a golf ball versus a soccer ball, right? A golf ball is much smaller, so is much, much lighter than a soccer ball. That's bigger, and I think the weight is a third power of the increase in radius. So what it means is that when people look at mass concentration, so microgram per cubic meter, like I was showing on those graphs, it will predominantly be because of larger particles, right? So when you say, oh, I'm going to look at PM0.3 and PM1 that I'm trying to filter and look at their mass, because that's what most sensor will give you, it will always be small because it's so light, right? So it's I wouldn't say false advertising, but if you say, oh, I have 1 microgram per cubic meter of PM0.3, well, I hope so, right? Because even if you have a lot of it, it's going to be super light. Versus PM10, you have few particles that will give you a higher mass. And so that's where the quality of the data and the sensor you use matters, because as research shows, a lot of the consumer-grade particulate matter sensor are really bad at measuring very small particles, and they make a lot of assumptions, and basically the numbers you get mean nothing, right? So when you're trying to say, oh, I'm going to filter those small particles, increase my filters, and then you just have garbage data to show you that, you can't do anything with it. And so it's really important to look at what sensors are being used, and there's a lot of research. I think AQ Specs is one of them that actually test the sensors on the field, compare them to very expensive equipment, and see the correlation of the data. And to add to the complexity, I don't know, I guess you guys are familiar with this type of chart. It shows you for different type of MERV filter how well it filters different size of particles, right? So a MERV 16, which is the black line all the way at the top, filters the best, but around 0.3 micron, which is the size that's the hardest to filter, you down to 70% efficiency. So I'll go back there. So the MERV 13 is the black line here, and you can see around 0.3 is the worst, and you're 70%. And then your regular MERV 8, it's this one, I think. So you're like at 10% filtration at those particle sizes. So that's why they recommend to use better filters. But even with that, it doesn't mean that because you're changing those filters, you're safe. So this graph just shows the same thing I was talking about. So this is inside a building, and it's the on the first graph is the distribution of particle size, and you can see how you have a lot more particle around 0.01 micron all the way to 0.1 micron. So it's really in that range, and above 0.1 micron you don't have that many particles because they're getting filtered, they're heavier, so they fall on the floor and stuff like that. But then if you look at the mass, it's the opposite story, right? Because of the mass, you have nothing below 0.1, and almost everything is, you know, around 1 micron. Does that make sense? So what? One more. So this is. So you remember the graph I showed you with the Class A building, the one at the bottom, and you couldn't see any black lines? Well, that's what's in the black line. So when I zoom in, this is using a expensive instrument that actually looks at the particle counts and whatnot. So the top graph, you can see there's like some blue, which is the 0.3 micron, black, which is 0.5, and then there's other colors. So you can see kind of all the colors in there, right? So that's the mass. But then you look at the counts, you can only see blue, which is 0.3. So same story. Most of the particles that are in the air are going to be those smaller particles that you can't really see in the mass, that are hard to filter, and that you really can't know it's there unless you have very good sensors to measure them. And so what's the impact of all that, you know, of this long story, is that we need to measure things. And you guys know it from commissioning. That's what, you know, you guys do, is making sure things that are installed are working properly. Well, now it's the same thing with indoor quality. We have to put in sensors to make sure that the measures that are taken, like changing filters, changing HVAC settings, have the correct impact on what we're trying to do, which is make the air cleaner and the space safer. The problem is that it has an impact on all the things that we've been trying to do for years, which is saving energy, right? So because you put, you know, higher filters, you're gonna have more strains on your HVAC equipment, so you're gonna consume more energy, it's gonna break faster, and then I'm gonna talk about this later, but you're also gonna change how much outside air you're having, how long you're running your HVAC equipment, and all that is gonna have an impact. And then I also mentioned building insulation, right? We try to make buildings tighter and tighter so that there's no outside air coming in. Well, that's great. So for example, you don't have particulate matter coming from the outside when it's polluted outside, but it also means that the air that's inside cannot go out, and the only real ventilation is mechanical ventilation. You don't really have natural ventilation anymore. And we actually seen in our research that when HVAC systems are not great, natural ventilation actually helps a lot. That's why, you know, one of the recommendations during COVID was open the windows. So the second use case I'm going to talk about is one of those, I wouldn't say new techniques because they were existing before, but something that really took off, and I'll spare you the controversy on this because there was a lot. I don't know if you guys familiar, but anyway, one of them being the NeedlePoint Bipolar Ionization. So as I said before, it's basically putting in the HVAC system something that generates ions, and those ions will, you know, spread in the space, attach to those small particulate matter I was talking about, making them heavier and easier to filter, right? So if they shift from 0.3, 0.5 to 1 and above, they're easier to filter. That's the theory. And so a lot of our customers came to us and said, okay, either we're selling these things or we want to install these things, how do we show it's working, right? And so that's what I have here. So in the first graph, okay, I'll start with this side. Try to make it fair. So, again, read anything. Okay, so the blue line is the ion levels, and the black is the PM 2.5, and the green is VOCs. So VOCs, again, I don't know if you guys know, it's total volatile organic compounds. So it's stuff in the air that have carbon. So it's chemicals, it's cleaning products, it's formaldehyde. It's stuff that some are harmful, some are not, but usually you don't want them. And so what we see is that when there is an increase in PM and VOC, you see a drop in ions. And again, there's a lot of controversy, and I'm not going to answer it now, whether it's working or not. This is just some of the data I gathered. So here you have levels, that drops quite a lot. But then when you reach a lower level in those PM and VOC, the ion levels go back to normal. In the second graph, the black line is the ions, the red line is the PM 2.5, and the blue line is the VOCs. And so we released VOCs, and you see how the ion level drop immediately, right? And then once the VOC level stabilize, the ion level go back to normal. But you can see there is absolutely no impact on the PM levels. And so from all my research, and it was not scientific research, do you guys need me to show this on this graph, or you got it? Good. From my research, the ions have an impact if you have events happening in PM and VOC. So if you have suddenly an increase in PM or an increase in VOC, you will see the ions have an effect, but not if you have a lower background level. Okay, so here you see it's not affected at all. So what does it mean? The problem with ionization is that it's in the HVAC system. So if your HVAC is not running, your ions are not going anywhere, right? So it means that it's only working if it's running. What does that mean? Is that people are going to make it run all the time. And that's not very energy efficient. And so, I forgot one graph, but quickly go over it. So this is in our office, 2 rooms. I'm measuring the PM levels. The blue line is the room that has ionization, the black line the room that doesn't. So when it's the same conclusion as before, is that when there aren't a lot of high levels of PM, you can't tell the difference, and it's almost like you have more PM in the room with the vaporization. But then when this is the same event when there were the wildfires I was showing at the beginning, it's the same timeline. When there are much higher levels, you can see the difference. Again, not scientific study, but interesting observation. And at the same time, you can tell the filtration in our office is not great, but I'm not responsible for it. So what can we do about that problem, right, is adding occupancy sensors, right? And so a big issue is that, when your building is already built, it's really hard to add new stuff. So this is one of the things we try to do is do easy retrofits where you can easily add those type of occupancy sensor so that you can really try to only operate your equipment when there are people in the space, right? Because now if you don't have people, you don't have virus, you don't have CO2, you don't have all these things. It doesn't matter if there's PM. So we see a lot of our customers trying to add these to kind of have an idea, okay, how many people are now in a specific space, and because modern buildings can really control HVAC on a pretty specific area, this is very useful data. Now, how long do you have left?
You have until 3:15.
Okay.
4:15.
Yeah, okay, we're good. So my third use case is CO2. Okay, so CO2 is more about ventilation. So as we breathe, we generate CO2, and if we seal this room, we don't have ventilation, the CO2 levels are just going to keep rising. And for a few years, I don't know, I'm not an expert, people realized that and started putting CO2 sensors in conference rooms and whatnot to make sure that it's ventilated when CO2 levels rise, not just because it's too hot or too cold or whatnot. But what was lacking is research on what's the impact of CO2, right? I think ASHRAE recommends to be 700 above outside air. So outside air is 400, so inside air should be 1100. Okay, so here's a study done in a school, not in a school, in an office building. And it's looking at 9 different cognitive tests and how do people do under different levels of CO2. So I hope you can't read the number here. I'm going to tell them to you after. So on the first thing, people, that's the baseline. For the second level, there was a 15% decrease in the cognitive scores for, I think, 7 out of the 9 tasks. And for the last one, there was a 50% decrease in cognitive numbers. So from here to here, 50% decrease. From here, the numbers are 400, so just fresh air from the outside. Number here is 1,000, so lower than ASHRAE, and the third one is 1,400. So 1,400, so from 400 to 1,400, most tasks, you see a decrease of 50% in the scores. Does that shock anyone? Fine? Okay. This is cool. This is 4,000. This number here.
That number's what?
4,000.
4,000.
Yeah, and the yellow line is 2,000. So we actually see a lot of spaces where it's always above 1,400. So it was just a study, right? I'm not saying it's the same thing everywhere, but for people who are here, are in classrooms and whatnot, where we don't measure CO2, it has a huge impact on the ability for people to focus, to retain information, and all these things. And so you see not a lot of states, some states like California, I think Maryland, are pushing to make it mandatory to measure CO2 levels in classrooms. So that's one aspect. The other aspect is CO2 is the main way to know if you have good ventilation in a space, right? Because CO2 is a contaminant that we know is there when people are there, right? You can try to hold your breath, but if you measure CO2, you know people are there. So by looking at the trend in CO2, the evolution of CO2, you can tell whether the HVAC is effective at removing those contaminants from the space. And if your CO2 levels are decreasing, it means that you're removing more of those contaminants that they are generated. So you can kind of draw parallels with, okay, if someone is sick and generating virus and stuff like that, are they going to be removed from the space faster than they're generated? That's the reason why with the pandemic, a lot of people just said, okay, we'll do 100% outside air. We'll bring as much fresh air from the outside that's supposedly clean, and we'll remove all this CO2, all this virus from the spaces. Again, the problem is that it had a huge impact on energy consumption, and we had a lot of customers telling us, well, ASHRAE says we have to do 100% outside air, but we know that we don't need to do it because there's nobody in the space, right? So how can we do it better? And that's why a lot of our customers started installing CO2 and indoor air quality monitors, is that now they can actually put a target in every one of their space on what CO2 levels they want to maintain by using sensor on supply air, on return air, and on outside air. And by looking at the ratios, they can actually optimize the percentage outside air, removing other factors like temperature and stuff like that, but simplifying. They can start optimizing when their HVAC is running based on this type of data. One of the challenges is that you can do this, you can have your dashboard and you can say, okay, I'm gonna make these changes, I'm gonna implement these changes, and I'm gonna verify that it works. But what people wanna do is automate, right? So how do we take that data and feed it inside the BMS without spending a fortune? And that's still a challenge today, is, okay, a lot of these BMS systems are closed, they're not connected to the cloud, and all the new technologies are connected to the cloud. So that's something we work through every day, but it's gonna get there. And it's all about, we see starting to have adoption, like big customers, Class A buildings are starting to do that, and now the rest of the industry needs to follow. But it's also becoming a differentiator for the customers, for the service provider or the building owners, to show that they integrate this type of data in their building management and their HVAC management, because it matters. Matters to people, matters to your health, and it's becoming really a thing in the industry. The last thing I'm going to talk about has nothing to do with HVAC, but it's more for something I wanted to mention, and for your own knowledge. So you may have, one of the things you may have gotten out of this presentation is that indoor quality is not straightforward. There's a lot of things to it. And vendors are trying to simplify things by talking about IAQ scores. So if you look at monitors, IAQ monitors, you will get, your temperature, your humidity, your VOCs, your PMs, your whatever, and then an IAQ score. You have to be really careful when you look at that IAQ score, because there's no industry standard. So if you look at the indoor quality, one of the only standards is the EPA as a standard for PM2.5 and PM10 for outdoor air, right? So it's outside exposure to particulate matter, and there are studies to show that the impact on our health. We spend 10 to 20% of our time outdoors, 80 to 90% indoors. There is not a lot of research on the impact of those different contaminants on our health indoors. And so what people are doing here is just say, okay, for my PM levels, I'm going to take what the EPA says for outdoors, I'm going to apply it indoors. Wrong. So that's for the PM. For the VOC and CO2, again, no standards. Yeah, you could take ASHRAE and say 400, 1100 and higher, but I showed you in the study that those numbers don't especially match with what's healthy. And VOC are another beast. Every single manufacturer, because VOC is a total volatile organic compounds, nobody can measure total. So they all are reacting to different things, and so you cannot really compare one sensor to another. So each vendor has to come up with their own thresholds for VOC levels. And then let's say you have one person in this room, okay, two, for my example, to work. So you're gonna have low CO2, they have good filtration, they don't have used chemicals, whatever. So you'll have a good indoor air quality score. And then the person has COVID and coughs in your face. Does it mean the indoor quality is good or not? Doesn't really. The problem is that these scores are missing a lot of other stuff. What about ozone? What about methane? What about carbon monoxide? So these are, it's not because it shows you a good IQ score that it means the air quality is good. It's not. So we need to have an industry standard for indoor air quality before you can trust any of these numbers. So takeaway is you have to look at the different contaminants, what they mean, what you're trying to achieve, and not just use a number to make you feel good. So that's really important, and trying to explain to our customers that it matters and it's not just about giving a false sense of confidence. So, in conclusion, I hope that I gave you this message that modern building management is changing. It's new types of data that need to be integrated into how we operate buildings, how we validate that the buildings are working properly. It's looking at other dimensions like indoor quality, like occupancy and stuff like that. And it's really not there yet. You hear about it, but most buildings don't have any of this. And so it's really critical, and depending on who you work with, we see a lot of architects are starting to integrate that into their design, having indoor quality monitors. So we see that the industry is changing. It really got accelerated because of COVID, which is maybe one of the things that came out of it. And it's going to keep changing. So hopefully I gave you like a crash course on this, and you've learned something. And so now I'll open it to questions. I think you need to get or you can scream, I don't know.
Yeah, if you have any questions, please raise your hand and I'll bring the microphone to you.
Forgive me if you already explained it and I didn't hear it, but could you go expound a little bit on NeedlePoint Bipolar Ionization? And you said, when there's an event or an elevated level, that's when you see it being more effective. Do you know what the mechanics going on there? Is it conglomeration, or what may be, the cause of that? It seems kind of counterintuitive.
Yeah, I have no idea. I'm not an expert in bipolar ionization, but yeah, it's a question I have for them. Yeah, I'm not sure. I don't want to talk about something I'm not.
Yeah, where you brought up the charts of cognitive function related to CO2 levels, where did that study come from?
You guys have access to the slides. There's here. You can go to this URL, and there's the whole paper there. I don't know, if you come after, I don't know, give it to you, you can write it down or something. But yeah, I think the slides are online. Yeah, for all I don't know if I have a lot of things coming out of papers, but when I take out of paper, I put the reference.
So if the technology is not there yet, what do you suggest we do in the meantime?
Which technology is not there yet?
Any of these indoor air quality sensors that are commercially available?
Well,
CO2?
So it's there with us, but no. So there are sensors that are out there that are really good. And you just have to, they're not all created equal. So you can just go buy the cheapest sensor you can find, especially for particulate matter. But if, for example, we always screen the market for new sensors. Because we're agnostic to sensor, we always integrate what we find the best. And there are really good stuff out there. You just have to be careful. It's not just buy anything and it will work. So for example, some of the low-cost sensor, the way it works, you can have multiple lasers, for example, counting the particles, and that's a lot more accurate. When air is humid, particles will get together. So if you look at outside air, you have to make sure that there's a mechanism in the sensor to heat the air, to dry it, stuff like that. So there are sensors out there that are really good and that are affordable. You just have to be careful, and we can help with that. And also, depending on the application, it's different. So if you do a hospital or a clean room or data center, you really care about the number of particles in the air in the very low ranges. But if you do an office space, it's less. You can have a different sensor, right? So we can help with that. But the technology is there for a lot of these sensors. It keeps changing, it keeps improving, but you need to know what you're doing. if that makes sense. But as long as you don't get garbage data, any data is better than no data. You just need to be able to interpret it properly.
My understanding, the CO2 sensor need to be calibrated pretty often.
It depends. So CO2 sensors, if you use them in a regular office space where you will reach outdoor air levels or close to that on a at least weekly basis, they have a system called automatic baseline correction, ABC, where basically it's going to look at the lowest level over a period of time and basically readjust in case there's a drift. And it works really well for any type of space that will be empty at some point. But if you work in a space where you might always have high CO2 levels, then it wouldn't work, right? Because it's gonna, I think that it's 400, it's actually 1200, and it's gonna be offset. So again, depending on the environment, you need to make sure you pick the right sensor. If you use a sensor that cannot use this ABC calibration, yes, you will need to recalibrate it once in a while because there will be a drift. So again, the technology is there, you just need to know which use case and pick the right thing. And again, we can help with that. Any other questions?
Any other questions?
Was it that boring? Or was it that clear?
Great information, Julien. Thank you so much for your presentation.
Thank you.